So hi everyone, welcome back to a very fresh session of chemistry. Yeah, back with yet another part, the part 2 of periodicity in elements. So hope you all are ready to face this part 2 of chemistry because you have studied. I hope that you have learned the part 1 very well. So in part 1 we have discussed about the periodic table, the evolution of periodic table, like how it came, who all contributed to the development of periodic table and what all were those contributions, like law of triads, law of octaves, the Obrainer. Many people came into the field, they researched, right, they developed new things, they put forward many theories about the periodic table, and finally we are here using the modern periodic table, right? So in our previous part, the part 1 of this chapter, we have discussed the evolution of periodic table, the properties of the currently using periodic table, that is a modern periodic table, right? The number of groups, the number of periods, the blocks, the number of blocks, and which are those blocks, SPDF blocks, and the outermost electronic configuration. Such things are going to be discussed in today's part. Like we are going to have a detailed discussion of SPDF blocks in today's part. Ready? Shall we go? And after this detailed discussion, we'll be discussing about the periodic trends in our periodic table. Like our elements are showing some physical properties, they have some physical properties, and how the physical properties vary along a period, along a group in periodic table. Such trends are going to be studied in a later time of this session, this part 2 of this periodic table, the periodicity in elements chapter. So shall we start? So S block, yeah, as I already mentioned, we have 4 blocks in periodic table. There is a S block, the P block, the D block, and the F block. So S block, which are the groups involved, group 1 and 2. And the last electron enters to the S subshell, last electron enters to the S orbital, hence they are called the S block elements. Group 1 and 2 elements are under S block. Group 1 are called alkali metals, group 2 are called alkaline earth metals. So S block is actually group 1 and 2. In that, group 1 is called alkali metals, group 2 elements are called alkaline earth metals. Ready? The general outer electronic configuration is NS1 to 2. NS1 to 2. Shall we see it with an example? Sodium 11. 11 is our atomic number. How are we going to write the electronic configuration of sodium? 1s2, 2s2, 2p6, 2, 4, 10, 3s1. This is a general outer electronic configuration. See, here it is S. The outermost shell is S. So it is a part of the S block element. Okay, here the number of electron is 1. As mentioned here, the general outer electronic configuration, the outermost subshell will be S, and in that 1 or 2 electrons are possible. Now coming to beryllium, it is simply 1s2, 2s2. Now the features of S block: highly electropositive elements, highly electropositive. Then low ionization enthalpy and very reactive. They are very reactive with other element, and also they are highly electropositive. They are willing to donate electrons. They are willing to become positive. How an element can become positive? By donating electrons, right? By donating electrons they become positive. By accepting electrons they become negative. So low ionization enthalpy. Ionization enthalpy will be discussed in the later part of this session. So they form ionic compounds. You know what is an ionic compound, covalent compound, like ionic bond and covalent bond. Everything you have studied in your standard 10. Also the oxidation status +1 or +2, as S block can have maximum value of 1 or 2 electrons. They either have +1 oxidation state or +2 oxidation state. Plus means, or plus is because the electropositivity of S block elements. Group number is same as that of number of electrons in the outermost subshell. Sodium 11, the electronic configuration is this. Is it either in first group or second group? How are we going to know about it. See the outermost electron. Okay, the outermost subshell is S and it has 1 electron, which means what? It is in first group. In the case of beryllium, the outermost subshell is S and the number of electrons in it is 2, which means it is in second group. So the group number is same as that of the number of electrons in the outermost subshell or the S subshell. Now the p block elements. So p block elements are usually in the groups of 13 to 18. Last electron enters the p orbital. Okay, 13 to 18. The 13th group is called boron family, carbon family for 14th group. 15th group is called nitrogen family. 16th group is called the oxygen family, and 17th group is called the halogen family, and 18th group, the last and final group, is called noble gases or inert gases. Inert gases, noble gases or inert gases for 18th group. So boron, carbon, nitrogen, oxygen, halogen and noble gases for groups 13 to 18. Okay, 13th group is boron family, 14th group is carbon family, 15th is nitrogen and so on. The general outermost electronic configuration is NS2, NP 1 to 6. And let's write the electronic configuration of oxygen here. Oxygen is the atomic number is 8. So 1s2, 2s2, okay, 2p4. 2p4. So the outermost electron enters the p subshell. Here 1 to 6 electrons are possible. 1 to 6 electrons are possible. Here 4 electrons are there. How are we gonna know the group number of p block elements? Group number is same as that of adding 12 to the number of electrons in the outermost subshell. Let's see how. Number of electrons in the outermost p subshell is 4. So 4 plus 12, add 12 to the the number of outermost electrons. So it is 16. So it is a part of 16th group. 16th group is oxygen family. So yes, of course, it's right. So add 12 to the number of electrons in the outermost p subshell. So that is all about p block. Okay, very low reactivity. S block elements have high reactivity, p block elements have low reactivity. They include metals, non-metals, and metalloids. They form ionic as well as covalent bond. S and p elements are together known as representative elements. Very important. S and p elements are together known as representative elements. So p block elements are in group 13 to 18. S block elements are in group 1 and 2. Now, yes, D block elements. Fine, let's see what are the properties of D block elements. Now, about the D block elements, the last electron enters the penultimate subshell. What is a penultimate subshell? Just the shell or the subshell prior to the outermost subshell. Consider this is a nucleus, n equal to 1, n equal to 2 and n equal to 3. This is the outermost subshell, and this is the penultimate subshell, and this is the anti-penultimate subshell. Clear? Outermost subshell, penultimate subshell and anti-penultimate subshell. In the case of D block elements, the last electron enters the penultimate subshell and groups 3 to 12 are part of the D block elements. And the outermost subshell electronic configuration, outermost shell electronic configuration is NS0 to 2, N-1D, 1 to 10. Let us write the electronic configuration of manganese here. Manganese, our atomic number is 25. So 1s2, 2s2, 2p6, 3s2, 3p6, 4:3d5. This is the outermost electronic configuration of, the electronic configuration of manganese, which is a part of d block elements because it enters the penultimate subshell. Penultimate subshell. The last electron enters the penultimate subshell, that is the d subshell. They are known as transition elements. They have high melting and boiling point. They show variable oxidation state. In the case of S block elements, the oxidation states were +1 and +2. Those oxidation states were fixed. In the case of D block elements, the oxidation states vary. They form colored and complex compounds. Compounds. Now, what are transition elements? Transition elements are what? Transition elements are D block elements. Okay, and they are part of the group 3 to 12. Right, the general outer electronic configuration. The general outer electronic configuration is already given here. Yeah, that's all. Coming to F block element, SPDF, the last block, the F block, the elements in which last electron enters the anti-penultimate shell, the F subshell of anti-penultimate shell. The last electron enters the anti-penultimate shell in the case of F block element. In the case of D block elements, it enters the the penultimate shell. Okay, there are two series of F block elements, lanthanoids and actinoids. As you already know, lanthanoids and actinoids are a continuation of period 6 and 7. Periods 6 and 7. They are a continuation of periods 6 and 7, and hence they are known as lanthanoids and actinoids respectively. The general outer electronic configuration is given here. The F block elements are also known as inner transition elements. D block elements are known as transition elements and F block elements are known as inner transition elements. They form heavy metals. They have high melting point, high boiling point. They form colored and complex compounds. They also show variable oxidation state. So they have many similarity with that of D block elements. As D block elements show variable oxidation state, D block elements also form colored and complex compounds. So there are many similarities between D and F block. The elements coming after uranium are called transuranic elements. Just know the point. Elements after uranium in F block elements, they are known as transuranium elements. Name the following group 18 elements. What are group 18 elements known as? They are known as noble gases. Group 17 elements. Group 17 are known as halogen family. And group 16 elements are called oxygen family. So, the P block, they are actually from 13 to 18, right? 13th group is boron family. Boron, carbon family, nitrogen family, oxygen, halogen and noble gases. That's all about the SPDF blocks. Now coming to the periodic trends. The periodic trends in our periodic table. The elements in periodic table depend on certain factors. They show certain physical properties like atomic radius, ionic radius, ionization enthalpy, electron gain enthalpy and many more. So in this class, we are going to learn about, or we are going to discuss some physical properties that the elements show and their change or variation along the period and along the group in periodic table. So in this class, we are going to discuss about the physical properties like atomic radius, ionic radius and electron ionization enthalpy. So starting with atomic radius, this is a nucleus, a shell, n equal to 1, n equal to 2, n equal to 3. What is atomic radius? Atomic radius is simply the distance between the center of nucleus to the outermost shell. It is the distance between the center of nucleus to outermost shell. So atomic radius is defined as the distance from center of nucleus to the outermost shell of electrons. Okay, the center of nucleus to outermost shell of electrons. And this atomic radius is divided into three, or it has three subdivisions, that is metallic radius, covalent radius, van der Waals radius. Let's see what are those types of subdivisions here. Starting with the metallic radius, I have an atom here, it's a nucleus. I have another atom here, sorry, I have another atom here, and the atom is just in touch with this atom. The atoms are just in touch. Remember that point? Just in touch. So the distance between the center of these two nuclei, taking their average or half of the internuclear distance will give you the metallic radius. Metallic radius is just a subdivision of atomic radius in which two metal atoms of a metallic crystal are just in touch, and the metallic radius is just the average or just the half of internuclear distance. So metallic radius is defined as the half of the internuclear distance. Half of the internuclear distance means what? Just the distance between these two nuclei of the atoms in metallic crystal. The atoms in metallic crystal are placed together, they don't overlap. They just touch each other, and the half of the internuclear distance, or the half of the distance between two nuclei, will give you metallic radius. Let's see the definition. Metallic radius, it is half the internuclear distance between metallic ions in metal crystal. It is half the internuclear distance of metallic ions or atoms in metallic crystal. Now coming to covalent radius. Covalent radius. Okay. Covalent radius is just simple. An atom here is here. Another atom is here. They are overlapping. So half of the distance between half of the internuclear distance of covalently bonded atom, it is covalent radius. Two covalently bonded atoms are here. The internuclear distance is denoted by this. Internuclear distance, distance between two nuclei. Taking half of the internuclear distance of two covalently bonded atoms will give you the covalent radius. Covalent radius, yes. Covalent radius is just the half of the internuclear distance between two covalently bonded atoms. Now the last one, van der Waals radius. Van der Waals radius is very simple. I have a molecule here. Molecule, you know what a molecule is, right? This is a nucleus of the molecule. I have another molecule here. This is a nucleus. So the distance between these two nuclei is the internuclear distance, and taking half or average of this distance will give you the van der Waals radius. In van der Waals radius, the two molecules are in van der Waals force of attraction. They don't have any other contact. But they are under the influence of van der Waals force. In such a case, the half of the internuclear distance will give you van der Waals radius. Van der Waals radius, it is half the internuclear distance between two non-bonded atoms of separate molecule. In the previous case, I have taken H2O molecule here. You can take any molecule in the solid state when they are under the influence of van der Waals force and they are not in contact or they are not in touch, the two molecules kept separately, then they will have the van der Waals radius. Now, variation of atomic radius in a period and in a group, along a period and along a group. Okay, fine, we will start with the variation of atomic radius along a period. In a period, the atomic number from left to right, when we are going from left to right, you know what a period is, right? A period is this, horizontal sections. Period 1, period 2, period 3. So, in a period, when you are going from left to right, atomic number increases. As atomic number increases, what increases? Electrons, number of electrons. Number of electrons increases. Will the shell number increase or decrease? Along a period, shell number increases or decreases? No, wrong. It remains constant. Shell number isn't changing. Because when period is 1, in period 1, we have one shell. In period 2, we have two shells. In period 3, we have 3 shells. It goes on increasing. So, along a period, shell number isn't changing. Shell number isn't changing. Shell number isn't changing. So, hence, as the electrons increases, as atomic number increases, but shell number is not increasing, hence the nuclear force of attraction increases. Nuclear force of attraction increases, atomic size decreases. As the nuclear force of attraction increases, it binds the electrons in the atom together. It just hugs. It hugs the electrons. It won't allow the electron to release or to go away. It will keep it together, reducing the atomic size. So, shell number isn't changing when we are going from left to right along a period. But what changes? The atomic number and the electron number. It goes on increasing. But the shell number isn't changing. So, electrons are getting placed in the respective number of shells. And hence, the attractive force of nucleus increases. It binds them together, or it keeps it together under the force of attraction of nucleus. So, atomic radius decreases along a period from left to right. Now, in the case of period going from top to bottom, in the case of group, when going from top to bottom, atomic number Z increases, electrons increases. What about the shell number? Yes, it increases as going from top to bottom. Number of period changes, shell number changes. Shell number changes or shell number increases. Then nuclear force decreases, hence atomic radii increases. Means what? Atomic size increases. The atomic size increases. When going from top to bottom of a group, the atomic number and hence the electron number increases. Number of shells increases. So electron is going farther and farther from the attractive force of nucleus. Hence the atomic size increases. Clear? All set? Now account for the following. This is a previous year question. Atomic size increases from top to bottom. How are you going to answer this question? Just keep these points in mind. When going from top to bottom of a group, what will happen? The atomic number Z increases. Don't use this symbol in answer sheets, just write increases, okay? Number of electrons increases, shell number increases, nuclear force of attraction decreases, hence atomic size increases. This is how you need to approach the question when given in your question paper. What about the sub question B? Atomic size decreases from left to right along a period. Is it true? We should account for that particular statement. When going from left to right of a period, you can change the same answer. Atomic number increases, electron number increases, shell number has no change. Nuclear force of attraction increases, hence atomic size decreases. Now, ionic radius. You know what an ion is, right? Ion, we have cation and anion. A parent atom, Z. When removing an electron, when giving an electron, it becomes Z plus 1 electrons. It removes or it donates an electron, it becomes Z plus. This Z plus is called as cation. Now, Z, when accepting an electron, it becomes Z minus. The Z minus is known as anion. So cations have positive charge and anions have negative charge because cations are species formed by removal of electron from parent atom. This is a parent atom in first case, Z. When removing an electron, 1 electron, when donating an electron, it becomes Z plus. So positive charge for cation. In the case of anion, negative charge is assumed. Negative charge is given for anion because Z, the parent atom, accepts an electron, it becomes Z minus. Negative charge, minus charge for anion. Ready? So cation is formed by removal of electron. Anion is formed by acceptance of electron. Now about their size, about the cation and anion size. Here, nucleus, I'm having an electron here. I'm having electrons here also. When I donate or remove this electron, what will happen? The atomic size decreases. So, size decreases for cation. Size decreases for cation. In other case, this is my nucleus, shell 1, shell 2. I have electrons here. Now I am accepting an electron. In the first case, the shell wasn't there. If I accept an electron, then what will happen? A shell increases, the electron will automatically be occupied in the second shell. In such a case, size increases for anion. Clear? So when comparing the size, the cation has smaller size than the parent atom, anion has larger size than the parent atom. The charge of cation is positive, the charge of anion is negative. Hope it's clear. In comparison to the parent atom, the size of cation is smaller but anion is larger. That is correct statement. Cation is larger but anion is smaller. Wrong statement. Cation and anion are equal in size. No way. There is always a donation and acceptance of electron happening between anion and cation. All the three are correct depending upon the atom. Okay. Isoelectronic species. What is isoelectronic species? What are such species? The isoelectronic species. Why are they named like isoelectronic species? Yeah, say the word again. Say the word again. It's iso. Iso means same. Electronic species. Yeah, some kind of species. They are isoelectronic. Means what? They have same number of electrons. Isoelectronic means same number of electrons. Let's see that with an example. Here, fluorine is there. The atomic number of fluorine is already given there as 9. The charge of fluorine is given as minus. Why minus? Yes, it is an anion. It is accepting an electron. It has accepted an electron here. So, as it has accepted an electron, negative charge has come. So, fluorine atomic number 9 when accepting an electron will become 9 plus 1 equal to 10 electrons. 10 electrons. Second case, sodium, the atomic number is 11. Positive charge is given, which means cation. It donates an electron. 1 electron is donated from sodium. So 11 minus 1 is 10 again. Oxygen, the atomic number is 8. But 2 minus is a charge seen there. 2 minus, which means what? It donates 2 electrons or accepts 2 electrons. It accepts 2 electrons. So 8 plus 2 equal to 10. Yeah, again. Nitrogen, the atomic number is 7. 3 minus is a charge seen along with nitrogen. So 3 electrons are accepted. 7 plus 3 equal to 10. In the case of magnesium, same way. Magnesium, the charge is 12. Sorry, the atomic number is 12. So Mg2 plus is given. 2 electrons are accepted. 2 electrons are donated. So the charge, the number of electrons are 10. Sorry, number of electrons is 10. See, all these species have same number of electrons. In the case of nitrogen alone, fluorine alone, magnesium alone, or sodium alone, they are not isoelectronic. But when they accept or donate electrons, they become N plus, N3 minus, F minus, Mg2 plus, similar way. So they have same number of electrons. Greater the nuclear charge, smaller will be the size. So in this case, which is having the smallest size? Obviously, cation is having smaller size. So we have 2 cations here, Na plus, Mg2 plus, which is having smallest size. Na plus or Mg2 plus? Yeah, Mg2 plus. Mg2 plus is having smallest size. Then comes Na plus. Then comes anion. Anion we have N3 minus, O2 minus, F minus. F minus will come first. Then O2 minus. Then N3 minus. Alright. This is all about the isoelectronic species. Which of the following ion is not isoelectronic with neon? So neon, the number of electron is 10 because the atomic number is 10. Oxygen, the atomic number is 8. When accepting an electron, it becomes 9. Sodium, the atomic number is 11. When accepting an electron, when donating an electron, plus charge, when donating an electron, it becomes 10 electrons. Aluminium, the atomic number is 13, 3 plus, it donates 3 electrons, so 10 electrons. Magnesium, the atomic number is 12, or 12 electrons are there, it donates 2 electrons, so 10 again. So all these are isoelectronic. Oxygen alone is not isoelectronic. Ionization enthalpy. What is ionization enthalpy? What is enthalpy actually? What is enthalpy? Enthalpy is energy. So what is the purpose of this energy here? For what purpose we are using this energy here? This energy is used here to remove an electron from outermost shell. This is a nucleus, n equal to 1, n equal to 2, n equal to 3. Here I am having some random number of electrons. I am having an electron here also. I need to remove this outermost, the electron in outermost shell. So as to remove this, I need to supply some amount of energy. This some amount of energy is known as the ionization enthalpy. Ionization enthalpy is actually the amount of energy required to remove the most loosely bound electron from the outermost shell of an atom. So smaller the magnitude of ionization enthalpy, it is easier to remove from the atom. Just nothing. As I have 2 shells only and I have an electron here. When I have an electron here, it is not easier to remove from the second shell, as the nuclear force of attraction will be very high. So when it is not easier to remove, I have to use more amount of ionization enthalpy. So when more amount of ionization enthalpy is used, it means it is difficult to remove an electron from the outermost shell. When I use little bit of energy, little bit of ionization enthalpy, or the value or the magnitude of ionization enthalpy used is less, it means it was easier to remove the electron from outermost shell. The unit is kilojoules per mole of atom. Kilojoules per mole atom. Factors affecting ionization enthalpy, it is atomic size, nuclear charge, shielding effect, penetrating effect, electronic configuration. Atomic size. How atomic size and ionization enthalpy is related? Along period, ionization enthalpy decreases or increases. Along period, we know that the atomic radius decreases, right? Atomic radii decreases. As the size is decreasing, it means that what? It means what? As the size is decreasing, the nuclear force of attraction is very high and it is very difficult to remove an electron from the outermost subshell, outermost shell. So we need to use large amount of ionization enthalpy. So ionization enthalpy increases. Along group, atomic radii increases, hence ionization enthalpy decreases. As the size increases, as the atomic size increases, it is very easy to remove an outermost electron, so less amount of energy is needed. Nuclear charge, just nothing. As nuclear charge increases, ionization enthalpy increases, because as the nuclear charge increases, it is very difficult to remove the electron from outermost shell. Shielding effect. Let's see what is shielding effect. Shielding effect or screening effect. You know the shield of helmets which you use, right? So what is the purpose of a shield? It protects, right? It protects something. So what is the effect or the purpose of shield in periodic table? The shield protects something or someone, right? In the case of periodic table, shield protects the outermost electron from the nuclear force of attraction. This is a nucleus. These are the shells. I have an electron here. I have some random amount or number of electrons here. So this particular electron is shielded or protected from the nuclear force of attraction or from the nucleus by the other nucleus, other electrons, the other electrons. So shielding effect is nothing, very simple, or the screening effect. It is actually the protection provided to the outermost electron from the nuclear force of attraction by the other electrons prior to the outermost electron. Prior to the outermost electron. Prior means before the outermost electrons. Alright. So the inner electrons create a kind of barrier that reduces the nuclear attraction, on outer electrons. So inner electrons act as a barrier here. Penetration effect means we have S, P, D, F blocks, right? S block is very near to the nucleus, so it is very difficult to remove an electron from S block. As the distance increases, as the distance from nucleus increases, it is easy to remove the electron. So that's just about the penetration effect. Now, along a period, we have learned that ionization enthalpy increases, right? So it is expected that beryllium and boron, beryllium has lower ionization enthalpy than boron, or boron has higher ionization enthalpy than beryllium. As per this, along a period, I have taught you that along a period ionization enthalpy increases. So as per that theory, boron is expected to have high ionization enthalpy than beryllium. But there is an irregularity. So let's see what's the irregularity in beryllium and boron. Beryllium is 4, boron is 5. The electronic configuration is 1s2, 2s2 here. Here it is 1s2, 2s2, 2p1, which is a stable element here. Is it beryllium or boron? Stable electronic configuration. Of course, stable electronic configuration is this, stable outermost electronic configuration, because S has 2 electrons, which means completely filled. Completely filled and half filled electronic configurations will be more stable. So beryllium is more stable than boron. Is it easy to remove an electron from a stable species? Is it easy to remove electron from beryllium which is stable than boron? No, never. So whenever a species, a substance or an element has stable configuration or completely filled or half filled configuration, it is going to have high ionization enthalpy. So in this case, beryllium has high ionization enthalpy than boron. It's just because of the fully filled or completely filled outermost electronic configuration. Now coming to nitrogen and oxygen, it is expected as per the theory that oxygen is having higher ionization enthalpy than nitrogen, because when going from left to right along a period, atomic size decreases and ionization enthalpy increases. But here, as per the above case or similar to the above case, nitrogen is having high ionization enthalpy than oxygen. How is it possible? Nitrogen 7, 1s2, 2s2, 2p3. Oxygen 8, 1s2, 2s2, 2p4. See this 2p3. How many electrons are possible in p subshell? 6 electrons, right? 6 electrons. So 3 electrons are already here, which means it is in half filled stable configuration. Half filled stable configuration. So this was in fully filled stable configuration or completely filled stable configuration. This was in half filled stable configuration. So whenever a element has half filled or completely filled outermost configuration, it requires high ionization enthalpy. Hope the topic is clear. We'll discuss the remaining topics in next class. Till then, bye.